Uno momento. Yeah.
In some cases with would you need to change
Sometimes. But again, don't worry about it. Don't worry about it. It's just one of those things that when you hear enough chemicals and you're rubbing shoulders with the sciencey people, they tend to they'll shorten things from 2 syllables to 1 syllable. But don't worry about it. Don't worry about being wrong or right. Just go pentaoxide, pentahydride. If Alexa was plugged in, I would ask her what it stands for. I'm just going to go ahead and say it says International Universal Pack of Chemists. Yeah, it's something along those lines.
I looked it up.
What does it stand for?
International Union of Pure and Applied Chemistry.
There you go. Pure and Applied Chemistry. International Union of Pure and Applied Chemistry. Yeah. When are we going to apply some chemistry? I know. The good news is after this unit, it's chemical reactions. Woohoo! Chemical reactions. Yeah. And we're doing games. There's a lot of games in this unit. I wrote some fun little activities. Okay. So hey, Austin. What is this? It is carbon monoxide. Chris, what is this?
That one is diphosphorus pentoxide.
No, this one.
That's not right. Give me a second. That's
Although, you know what?
dioxide.
Yeah, it is carbon dioxide. You were right about that one, by the way. Seth, what is this? Hey, guys, can you please be quiet? Yeah, the same. Thank you, Seth. Seth, what is this? Boron trifluoride. Good. Maddie, what is this? Carbon tetrachloride. Julian, what's this?
Diphosphorus pentaoxide.
Excellent. Diphosphorus pentaoxide. Diphosphorus pentaoxide. Scott, what's this? Oh, I didn't even mark him acid. Joe, what's this? Nitrogen dioxide. Good. And Adam, what's this? Almost. The first thing doesn't have its name changed. So it is di. Close. Dinitrogen. 4 is tetra. Is that what you said?
Yeah.
I'm sorry. I'm sorry. I thought you were saying something else. Well, if you people would stop talking. So yes, thank you. Dinitrogen tetroxide. Keely, what's this? Excellent. Trinitrogen pentoxide. Oh. Sarah, what's this? Not here? Not anymore. Yeah, that's like, why is that one still in there? Michael, what's this?
Dihydrogen oxide.
Close. Dihydrogen monoxide. Dihydrogen monoxide. And Daphne, what's this? Excellent. Sulfur dibromide. And right. And Anthony Smith, what's this?
Silicon dioxide.
Silicon dioxide. And Chloe, what's this?
phosphorus trichloride.
Awesome. Okay. I should really update my cards. Okay. Hey, it's the cards. It's the luck of the cards. Okay, give me a thumbs up if you're ready to move on. Give me a thumbs down if you want to go over it again. All right, moving on. Now, remember how I told you we're going to skip over the D block metals because they are multivalent? Yeah. They can be all sorts of goofiness with that electron C. They're like, man, my electrons we share them with everybody. Can anyone truly own their electrons? So the D block metals, they're sharing their electrons, so they can have any charge, any oxidation from +1 to +7. Now, when you take chemistry AP, you'll learn about what is most likely to occur. But just know that at this point, the D block metals can be anything from +1 to +7. And it's not even like +1 on that side, +7 on that side. Titanium could be +4, and copper could be +2. So it's any charge from +1 to +7. So you have to have a way to tell your audience what metal you're dealing with. Let me show you what I mean. I'm going to turn the light back on. If I asked you for iron oxide, you might come back and bring me Fe, we'll just say Fe2O. Or you might come back and bring me Fe2O3. These are both iron oxide. So how do you know which one I asked you for? If that one's black and that one's brown, I could say, bring me the brown iron oxide. But we can't necessarily do that. So instead, we use Roman numerals. 1, 2, 3, 4. IV is 4, 5, 6. And we can go on and on and on. We can put 7 in there. 7 would be VII. And that's as far as we go. Okay? So we can use Roman numerals to say, this is the charge of this iron. Let me show you what I mean. Oxygen's common ion is what? -2. Remember our oxidation states? Follow the little green dot, which is little green dot got gigantic apparently. Apparently it dropped and got out of whack. So +1, +2, +3, +4, -4, -3, -2, -1, and 0. So oxygens hang out in group 16, has 6 valence electrons, it is -2. So oxygen has a charge of -2. The most important rule in making compounds is the overall compound has to have a charge of 0. I'll say that again. The most important rule in making compounds is the overall compound has to have a charge of 0. So if oxygen is -2, then there's a -2 for the negative side. The positive side should be what? +2. How many irons make up that +2? 2, which makes each iron +1. We would write this as iron 1 oxide. Okay. Sometimes you see the Roman numeral put in parentheses. I'm not a fan of that, but you do see it. So this is iron 1 oxide. Let's apply the same logic to this one. Oxygen has what charge? -2. And how many are there? Yeah, for a grand total of -6 on the anion side. That means the cation has to be how much? Has to be +6. Because again, the most important rule is the whole compound has to be 0. The cation side has to balance the anion side. How many irons make up that +6? 2, making each iron +3. So we would write this as iron 3 oxide. Okay. Can you see what's going on here? Can you see the pattern developing? So the D block metals, because they can be pretty much anything from +1 to +7, we have to tell the audience this is what non-metal, or this is what metal you are using. And you use a little basic arithmetic to say, based on what I do know, the non-metals, I'm going to use that information to find out what I don't know, the metal. Okay. Does this make sense? All right. So we will practice this more next week. But again, we use Roman numerals for the D block, and only the D block, except the P block that have D block electrons like magnesium, thallium, lead, that kind of stuff. Question? Okay. So yeah, just the D block And then metals, big heavy metals that had D block electrons. Those are the only ones we use it for. We don't use them for S block metals. Okay, so this would be written as iron 2, iron II. This would be cobalt III. Cobalt III. And then tin 4, chromium 6. Yeah, that's what all those I's were on there. Why you write all those I's on that periodic table? Really? Well, I added them to remove the confusion. Hopefully you'd figure out that oh, those I's need to be in there. Okay, here's the trap, guys. Are you ready? Here's the trap you will fall into if you're talking to your neighbor instead of paying attention in class. Ooh. Yeah. Sick burn. Okay, so the Roman numeral does not show you how many you have. It shows you the charge on each of those D block metals. Not how many you have and not the overall charge. It shows you the charge of each of those Roman numerals. So this is not iron 2. It's not iron 6. It's iron 3. It's not iron 2. It's not iron 6. It's iron 3. There are 2 irons. That's true. The irons balance out to +6, also true. But each iron is +3, so we're going to call this iron 3 oxide. Okay. Rattling around between your ears, does that make sense to you, what I just did? Okay, doing it again. The Roman numeral tells you the charge of each of the metals, not how many you have, and not the overall charge. So Fe2O3 is iron oxide, and it's iron 3 oxide because each iron is +3. It's not iron 2 oxide because there's 2 irons, and it's not iron 6 oxide because there's an overall +6. It's iron 3 oxide because each iron is +3. So you might think of it as this is +3 and +3 balanced out by a -2, a -2, and a -2. Okay, question?
Okay, what if you had like Fe4O6 and they were both iron 3 oxide? How would you differentiate between those two?
The good news is Fe4O6 wouldn't exist because it's a multiple of Fe2O3. So thermodynamically, Fe2O3 would exist and keep Fe4O6 from existing. But good question. Okay, the rest of this is pretty obvious, so we can just skip it. Okay, review of oxidation number. Okay, review of oxidation number. So if you follow a little green dot, again, we've been doing this for the last couple months. Everything group 1 is what? +1. Everything group 2? Everything group 13? Carbons group? Nitrogen's group? -3. Oxygen's group? -2. Fluorine's group? -1. And our noble gases are, of course, 0. So, when you guys, I realize, like, but there's 3 minutes left. We have to pack up. I'm very slow. No, pay attention. When you are asked the oxidation of something, you give the oxidation of each atom in a compound. For instance, water is H2O. Okay. Oxygen is -2. Hydrogen is +1. But there are 2 of them. There has to be 2 of them to balance it out. But oxygen is going to be -2, so hydrogen is going to be +1 each. Make sense? All right. So, rule number 1. Most important rule, the total oxidation of a compound must be 0. If you can hold it in your hand, it's going to have an oxidation of 0. If you can see it, it's going to have an oxidation of 0. If you can throw it at your neighbor, it's going to have an oxidation of 0. Okay. You cannot hold ions in your hand. If you're going to hold it, if it exists, that you can see it, you can hold it, it has to have an oxidation of 0. Second rule, any free element has to have an oxidation of 0. The oxygen you're breathing in right now, oxidation of 0. The nitrogen you're breathing in right now, oxidation of 0. If you were to run around with a stick of copper, you're like you have a copper metal, I have a copper sphere or a bar or a handful of copper, each of those copper atoms has an oxidation of 0. Okay. Make sense? So this aluminum track, all the aluminums in here have an oxidation of what? 0. 0. If this was just, if these coils were just iron and not steel, if they were iron, then all the iron atoms in there would have an oxidation of 0. Now, the cellulose that makes up this wood, the cellulose compound has an oxidation of what? 0. Okay? Each of the elements might not, but the overall compound would have an oxidation of 0. Okay. Give me a thumbs up if this stuff makes sense to you. Question.
So, do humans have an oxidation?
Your overall oxidation of you as a person, all the elements that make you up, all the compounds that make you up, would have an oxidation of 0, so you'd sum them up to 0. This is, yeah, question?
So the oxidation of free element is 0, so I know so hydrogen doesn't have an oxidation.
Hydrogen would be +1 or -1 until it became hydrogen gas, then it would be 0.